equilibrium constant practice problems. So when we have these types of questions, we need to ask ourselves, do I need an ice table? Why or why not? If we have any initial information, then yes. If we have initial concentrations or any initial numbers, then yes, you need an ice table. If all of the information that has been given to you is about equilibrium concentration, then no. But this has to be all information is in equilibrium. Then you don't need an ice table. So let's analyze this problem. So this problem says that we have 1.0 moles of hydrogen gas and 1.0 moles of fluorine gas are sealed in a 1 liter flask and allowed to react. So this is allowed to react, which means that this is initial. Then they give us an information about equilibrium, but only for hydrogen fluoride. So we only have one information about equilibrium, and the rest are initial information. So therefore, yes, we need an ice table for this problem. Okay. Now that we've established that we need an ice table, we need to place the given values in their appropriate location on our ice tables. So we have here information about hydrogen gas, fluorine gas, and hydrogen fluoride gas. Okay. Make sure that they're in moles per liters before I fill in anything else. Okay. And that we start with the column that has two sets of information. In this case, the hydrogen fluoride has an initial and an equilibrium information. So I can find the change information by doing some calculation. So I know it started with 0 because it wasn't mentioned, so we assume that it's 0. Therefore, the change must be an increase of positive 1.5. Now that I have an information for a change, I can then use my molar coefficients to find the other change values. Notice that the change values are dependent on the molar coefficients. So this 0.78 is because the 1.56 is a 2-to-1 ratio. Therefore, this is going to be half of 1.56. Also make a note that the symbols for my products are always opposite of my reactants. So if the products has increased, both my reactants should decrease. And then I follow each column into completion. And now I have all the information I need for the calculation of my equilibrium constant, because I need equilibrium informations to calculate for this Kc value. And all I need is to find products over reactants and plug these values into my expression, noting that the exponents are my molar coefficients. Once I've done that, my straight calculation is 50, following and noting significant figures and no units for the Kc value. So try this on your own. I'll give you time to complete it or stop the video and then resume the video once you're done so that I can show you each of the steps. So once you've read it over, and read it a few times to make sure you know which one's initial, which ones are at equilibrium, whether you need an ice table or maybe you don't. Okay, so let's answer the first part. Part A, write a balance equation for the reaction equilibrium. Okay, so I have 1 carbon monoxide gas plus 1 water vapor gas and 1 carbon dioxide gas and 1 hydrogen gas is produced. So we have products and we have reactants. Also note the states, because remember that if I have solid species, then it's not part of my equilibrium calculation. If I have liquid water, that's not part of my equilibrium calculations. But notice that all of these species are gases, therefore I can put them in my expression, all of it. So note water is involved because it's in a gas form, but if this was liquid water, I will just take this out of my expression. Determine the initial concentration of the reactants. I need to change 500 mils to 0.5 liters. And each reactant, okay, each reactant is in this container And each reactant is 2 moles, so each reactant is going to be 4.0 moles per liter. Next, we produce an ice table because we have some initial, and they've given us that the final equilibrium concentration for hydrogen is unknown. So in this question, they gave us an unknown value for the equilibrium, and therefore if it is unknown, we give it a variable x. I trust that you're okay with working with variables. So now we start at the column that has 2 sets of information. In this case, we have the hydrogen gas starting at 0 because it wasn't mentioned, so we assume 0 at the beginning, but we don't know its concentration x for its equilibrium concentration. But we have enough information to find the change. How did it get from 0 to x? So it must be a plus x. Now that I have a change information, I used my molar coefficient, which luckily is a 1 to 1 to 1 for all of them. So that's an easy one to note. All of them are x's. But make a note which ones are positives and which ones are negatives. So if it is a product and one of the product increases, the other product will also increase. If the products are one set of signs, the reactants are the opposite signs, negative. Then we complete the chart. Now we have equilibrium expressions. We have equilibrium values. So all these that are under equilibrium is what we use for the equilibrium constant Kc. These are the values that I will plug in. So now that I have these values to plug into my expression, okay, I substitute it in. They've given me Kc as 4.20. I plug them in, check and recheck. Then I know since the bases are the same, I can combine the exponents and add them. The bases here are the same, therefore I can combine them. The exponent is added. So are we okay here that now, at this stage, I can square root both sides, squared term, and I can square root both sides to get the x to an exponent of 1. Okay. And then I cross multiply and distribute this value, okay, to isolate for x. And then I do my algebra, isolate from my variable, and it gives me an x value of 2.68826239. Note that this value is not necessarily my final answer. X is only the answer for the concentration of hydrogen and carbon dioxide. X is not the answer for the concentration of water gas and carbon monoxide gas. So then I take this value and plug it into my table, and now I get that my carbon monoxide gas concentration is 1.31, which is the same as my water vapor, that my carbon dioxide is 2.69 to proper significant digits, okay, and my hydrogen gas is 2.69, all in moles per liter. Okay, so now you got to be careful that if it asks for concentration, your answer should be in moles per liter. That's a concentration. Sometimes they're going to ask you for the chemical amount. If they want the chemical amount, they're actually looking for just the moles. So if I was looking for the chemical amount of each of these substances, I'm now giving the concentration. I'll use the concentration and multiply and get rid of the volume component. So whatever liters I have, my container size, I will multiply these numbers by that volume size to get and isolate my moles. For my chemical amount is moles. My concentration is mole per liter. So make a note, this method can only be used if the reactant concentrations are the same. If the reactants have different concentrations, a quadratic formula will be required, which is beyond the expectations of this course. Okay, so you don't need to do a quadratic formula, but if you want a very exact answer, you can, but most of our answers is the rounded value, okay? So we don't need the quadratic formula. You can do it for fun and for information, but not necessary. Okay, let's try this on your own. So stop the video and then play the video again once you want me to show you the step-by-step calculations. All right, so this is the solution. So if you're not quite done, then keep pausing the video. So step 1, place it in an ice table because I have some information that was introduced, which is an initial value, and I only have one information about my equilibrium. Okay, so therefore I need an ice table. Okay, remember I don't need an ice table if everything is in equilibrium already. Okay, so here we have our given information placed where they're supposed to be. Okay, everything is calculated in moles per liter. The container is 2 liters, so therefore I divide all my moles by 2 liters to get my moles per liter and put them in their proper location. So this one is for N2O4 dinitrogen tetraoxide. It has 2 sets of information, so this is where I will start. So the change that I would calculate is negative 0.20. Okay, so I'm going to use this up, and therefore my nitrogen dioxide is going to increase, and I can use my change of 1 to 2 ratio to now note that it will increase by double that, 0.04. I assume it has 0 moles per liters at the start because it wasn't mentioned, and then I calculate that it's 0.4. Then I use these values to put into my equilibrium expression that I know is products over reactants. And my product is nitrogen dioxide. My reactants is dinitrogen tetraoxide. Put this in their proper values with their proper exponents. And substitute them. And then calculate with a Kc value of 0.2. Hopefully it starts to get easier. Okay, practice and maybe send me some email if you have questions. Then we move on. Next. Again, I'll give you some time to pause the video so that you can do this on your own, and then play the video again once you want to see the steps to solve this problem. Okay, so again, let's read to see if we need an ice table or not. A 10-liter bulb is filled with 4.0 moles of sulfur dioxide, 2.2 moles of oxygen gas, and 5.6 moles of sulfur trioxide. The gases then reached equilibrium. So this meaning that then reached means that these informations were initial information. So if we have any initial information, we need an ice table. And then when we read at equilibrium, the bulb was found to contain 2.6 moles of sulfur dioxide. So we only have one information on sulfur dioxide. And note, everything that they've given us is moles, but it is in a container of 10 liters. So let's place them where they should be. All the information that's pertinent that's been given to us is now calculated in moles per liter for all of them. Everything was divided by 10. Okay. Then we start with this column because it has 2 sets of informations. So I can use the change. Here the change when I do the math is negative 0.14. So if the reactants are decreasing, this will also decrease negative, and this will increase the product. So using our molar ratios, these are my values. Okay, next, then we complete the columns by doing the calculation through each column. And then I have all my equilibrium calculations complete. And therefore, I can now place these values. These are the only values I put into my equilibrium expression. Products over reactants. Then we have them properly placed so that I don't make a mistake. Proper substitution with proper exponents. And therefore, my Kc value with 2 significant digits is 48. Okay, hopefully you got that right. Next. So again, pause the video. So this one's, okay, it's very short, but it's a little bit more complex. So make sure you make a note of this, please. So once you're ready, you can play the video again or stop it still if you still need more time. Okay. So determine the equilibrium concentration for all the species given that the initial concentration. So again, they gave us something initial. Therefore, I need an ice table. So given everything is in moles per liter, so I didn't need to calculate this. This is already in moles per liter for my reactants. Each reactant is the same. Nothing was mentioned about the product, so I will assume 0. Note that that's all the information they've given us. Okay, nothing else is given. No equilibrium concentration is given. Therefore, we have unknowns. Okay, so we look at the box. That's the easiest one to figure out. Okay, since we have a 0 start, it's easy to know the change. Okay, our math is going to be simpler if I have an unknown variable in this column, because the change is going to be a plus x to get to x. Okay. Then we use our molar ratios. So if I have x and this is 2 to 1, this x is twice as big as this, so this must be half an x. If the x is a positive, this negative half an x makes sense for my reactants. And then I just solve them like normal, but using algebra this time. I now have this for my equilibrium expression. So these are the values that I will plug in into my Kc calculation. So products over reactants, this is my expression. This is now my substitution with proper exponents. Here, my substitution just happens to have a lot of unknowns. So now that I clean that up, that this is my expression that you just saw over here, I'm just cleaning up to make more room. They've given us Kc of 0.00250. So since both of them are Kc, I can do an equation between these two expressions. Then I solve these expressions, just like I would do in math class, grade 9 and grade 10 math C, 10C. Square root it, cross multiply, isolate for x. Now x in this case is only the answer for the concentration of nitrogen monoxide, okay? But x, I need to plug it in to find the concentration of nitrogen gas and oxygen gas. Once I've done the substitution, these are now my values. Okay, it's just long, it takes patience, but it's not hard. Try this one. Okay. So this question is page 689, number 10 in your textbook. So we have to consider the reaction system of 2 hydrogen bromide dissociating into hydrogen gas and bromine gas. So we have initial. So right away, if I have something that's initial, I need an ice table, because I need to find the concentration at equilibrium, and they didn't give me any information at equilibrium, and calculate the chemical amount. Remember, there's a difference between concentrations and chemical amount that we need to discuss. Okay. So look at our ice tables and I place where my givens are in the proper location with their proper units. Need moles per liters for this one. Okay. No other information is given regarding the changes, the C value and the equilibrium, my E value. Since the changes are based on molar ratios, we can start here with the unknown X. We know that we cannot have a negative concentration, so the HBr must increase because I don't have a negative concentration ever. So we know that this can't get lower, so I can only increase, but I don't know the amount of increase, so I will increase this. And if this is an increase, these other two must be a decrease. Since now we have a 1 to 1 to 2, the increase and decrease, I'll make it easy for myself. And note that x, since I didn't know the decrease, I'll make that x. And I know I need to double that for my HBR, and it's a positive 2x because it needs to increase, and this must decrease as a result. Okay? And then we do normal calculations. Now that I have my equilibrium that I can substitute in my expression, because my Kc value is given, I make sure I've substituted appropriately products over the reactants using the equation given to me. Okay? And then it's just a matter of substitution and being careful with your exponents and your brackets in your calculator and distribution and cross multiplication, and make sure your x is 0.389 if you're using this value. And then once you do that, you now substitute x into these, okay, because x in this case is not any answer. Okay? So when I do my substitution, I find the concentration for HBr is 0.78, for hydrogen gas, 0.11, for bromine gas, 0.11 moles per liter. Concentrations are measured in moles per liter. The next one that we're going to find is calculate the chemical amount. The chemical amount is the number of moles. Therefore, the chemical amount at equilibrium is going to be moles per liters times the container volume, which means these are in moles only of each species. It's long, but it's not hard, okay, to figure out. Be patient and show your work.